There are different types of capacitors. Depending on the type of dielectric used and the type of construction, capacitors are classified. Okay. Different types of capacitors are not there in your syllabus, but still it is worth knowing. So this is a ceramic capacitor. You can see two leads with disc. Here also two leads with disc. Capacitor has two terminals. You know that. This is electrolytic capacitor. It is also called aluminum electrolytic capacitor. Okay. Cylinder type and polarity is mentioned. Tolerance voltage is also mentioned. This is carbon film capacitor. Ceramic capacitor, carbon film capacitor, electrolytic capacitor, now combination of capacitors. This is circuit symbol of a capacitor and this is circuit symbol of a cell. This is cell, this is a capacitor. Series combination of capacitors means this is one capacitor, second capacitor, third capacitor. If capacitors are connected like this, end to end, then these capacitors are said to be connected in series. Suppose if this combination is connected to a battery, multiple cells means battery, combination of cells is battery. Okay. So if these three capacitors are connected to a battery, this is positive. Therefore, this side takes positive charge and the other side takes negative. Plus, minus, plus, minus. So in series combination, you should observe plus, minus, plus, minus, plus, minus series. And also, if capacitors are in series, charge stored in each capacitor is same. Charge on this plate is plus Q, charge on the other plate is minus Q. Recall, total charge on the capacitor is 0. Here also total charge is 0. This is plus Q, this is minus Q. Similarly, plus Q, minus Q, plus Q, minus Q. So charge in a capacitor means charge on each plate. So charge in each capacitor is same if they are connected in series. If this is 12 volt, then potential difference across first capacitor is 4 volt. Capacitor potential difference across the second capacitor 4. Potential difference across the third capacitor is 4 volt. So sum of these three voltages is equal to the applied. So if this is denoted by V1, this is V2 and this is V3, then V1 plus V2 plus V3 equal to the applied. Let this voltage be V. Similarly, parallel combination. Parallel combination means this is first capacitor, this is second capacitor, and this is third capacitor. Left terminal of all these capacitors are shorted. Shorted means connected by a wire. Right terminals are shorted. Means these three capacitors are connected across A and B. Meaning of this statement, one end of the capacitor is connected to A. One end of this is also connected to A. One end of this is also connected to A. The other end is connected to B. This is connected to B. This is connected to B. Then these three are said to be in parallel. When capacitors are in parallel, then potential difference across them is same. If potential difference across the first capacitor is 12 volt, second capacitor is also 12, third capacitor is also 12. But charge in each capacitor will be different. If this is Q1 plus Q1, the other one is minus Q1. This is plus Q2. The other plate will take minus Q2 plus Q3 minus Q3. Under special case, charge on this plate can be equal to charge on this plate. In general, charge on each plate is different. Here charge is same, potential difference is different. Here potential difference is same, charge is different. Students, in high school you have read about resistors in series. Like this. Am I right? Similarly, here capacitors in series. There again in high school, resistors in parallel. Resistors in parallel means first resistor, second resistor, third resistor. Resistors in parallel means something like this. First resistor, second resistor, third resistor, all of them are shorted like this. So this is parallel combination of resistors. Here parallel combination of capacitors. Series, parallel. Capacitors in series. Two capacitors are said to be in series if they are connected end to end such that charge stored in them is same. Consider two capacitors of capacitances C1 and C2 connected across a battery such that V1 and V2 are the potential differences across them. These two are two capacitors in series connected across this battery. Charge on each plate is Q plus Q minus Q plus Q minus Q. This is positive, therefore this plate takes positive charge, other takes negative, positive, negative. Potential difference across first capacitor is V1. Potential difference across second capacitor is V2. Let us write like this. So potential difference across first and second. In series combination, charge in each capacitor is same and V1 plus V2 equal to V applied. V equal to V1 plus V2. But Q equal to CV or V equal to Q by C implies V1 means potential difference across first capacitor is Q by C1 and V2 equal to Q by C2. Let us substitute these two in this equation. Therefore, V equal to V1, V1 is Q by C1, Q by C1 plus Q by C2. Let us take Q common factor, Q Remaining is 1 by C1 plus 1 by C2. Therefore, V is Q into 1 by C1 plus 1 by C2. Let this be equation 1. The capacitors are replaced by a single capacitor called the equivalent capacitor. For the equivalent capacitor, suppose this is the equivalent capacitor, which when connected across the same battery should store the same charge. So this is plus Q, this is minus Q, potential difference is V. So this capacitor CS stands for series equivalent of capacitors. For the equivalent capacitor, V equal to Q by CS. This is equation 2. So from equation 1 and equation 2, equation 1 is Q into 1 by C1 plus 1 by C2, isn't it? And equation 2 is Q by CS, or CS equal to one by CS equal to 1 by C1 plus 1 by C2, or CS equal to C1 C2 by C1 plus C2. Take LCM, simplify. CS equal to C1 C2 by C1 plus C2. In general, 1 by CS equal to 1 by C1, 1 by C2, etc. plus 1 by Cn. This is for n capacitors connected in series. Capacitors in parallel. Two capacitors are said to be in parallel if they are connected across two common nodes such that potential difference across them is same. Consider two capacitors of capacitances C1 and C2. Connected in parallel across a battery such that Q1 and Q2 be the charges in them. These two are two capacitors in parallel connected across this battery. These two are the nodes. Node means it is a point in the circuit where two or more conductors meet. This is C1, capacitance of second capacitor C2, charge on this plate plus Q1, charge on the other plate is minus, it is Q1, in this case plus Q2 and minus Q2. Since these two are in parallel connected across this, if V is the potential difference, here also V is the potential difference. V is potential difference across the capacitors. In parallel combination, potential difference is same and sum of these two charges Q1 plus Q2 is the total charge. In parallel combination, potential difference across each capacitor is same and that is equal to V, and Q equal to Q1 plus Q2. Sum of these two charges is the total charge. But Q equal to CV implies I want Q1, therefore Q1 equal to C1V and Q2 is C2V. Therefore total charge becomes C1V plus C2V. V is common factor, C1 plus C2. This is total charge Q. Equation 1. Now the capacitors are replaced by a single capacitor called the equivalent capacitor. The capacitors are replaced by a single capacitor called the equivalent capacitor. For the equivalent capacitor, Q equal to C parallel into V. This is equation 2. CP is parallel combination. So if this is the equivalent capacitor, single capacitor, which when connected across the same battery should store same charge. That same charge is Q1 plus Q2. Okay. So from 1 and 2, CPV equal to V into C1 plus C2 or CP equal to C1 plus C2. In general, for n capacitors in parallel, CP equal to C1 plus C2 plus C3 plus Cn. Series equivalent of number of capacitors is always smaller than the smallest capacitor. Meaning of this, if this is first capacitor, second capacitor, third capacitor, and this is 6 nanofarad, this is 3 nanofarad, and this is 2 nanofarad. If you find the series equivalent of these three capacitors, it turns out to be 1 nanofarad. You will understand how we got 1 nanofarad. And observe, this 1 nanofarad is smaller than the smallest of these three values. So among these three, 2 nanofarad is the least. And even this is smaller than the smallest. That is the meaning of this first note. For 3 capacitors in series, one by Cs equal to 1 by C1 plus 1 by C2 plus 1 by C3, or Cs equal to C1 C2 C3 C1 C2 plus C2 C3 plus C1 C3. So this is how you should use if 3 capacitors are given. You can use this formula or directly use this. And which is the common mistake means, when we solve this, we think that CS is C1, C2, C3 by C1 plus C2 plus C3. So this is the common mistake. This is not the answer. This is not the required equation. That is the second note. If two identical capacitors are in series, then series equivalent is C by 2. Meaning of C by 2? If this is first capacitor, second capacitor, each equal to 3 nanofarad, identical capacitors, then CS equal to 3 nanofarad capacitance of each divided by 2, that is 1.5 nanofarad. Extending this argument, we can write for n identical capacitors, series equivalent is C by n. First capacitor, second, third, fourth, this is 2 nanofarad, 2 nanofarad, 2 nanofarad and 2 nanofarad each. Then series equivalent of these 4 capacitors is CS equal to C by 4. C is 2 nanofarad by 4 equal to 2 by 4 is 0.5 nanofarad. So this is how you can use this formula. If there are n identical capacitors in parallel, then CP, parallel equivalent of n identical capacitors, it is n times C. This is first, second, third, fourth. If these 4 capacitors are in parallel, let each equal to 1 nanofarad. 1 nanofarad. Identical values, identical capacitors in parallel means CP equal to, there are 4 times each equal to 1 nanofarad equal to 4 nanofarad. So this is how we can use. In the next video, let us see different combinations of capacitors and how to find equivalent capacitor.